for being here. My name is Coblentz. I'm a PhD student at Oregon State University. And today I'm going to talk a little bit about disruptive selection. So disruptive selection, you'll remember from, say, your Intro to Evolution class, is a form of natural selection in which individuals with extreme trait values at either end of some distribution have higher fitness than individuals at intermediate trait values. And so why is disruptive selection important? Well, it influences a lot of evolutionary and ecological processes. So for example, most models of sympatric and ecological speciation require disruptive selection. And furthermore, disruptive selection is important in maintaining genetic and phenotypic diversity within species. And we know that genetic and phenotypic diversity have a variety of effects. From some examples with salmon, where that might help them resist extinction, to diet diversity and things like sea otters. So what drives disruptive selection? Well, one example that's been really well studied theoretically is that disruptive selection is driven by interspecific competition. So how's this work? So we can assume that there is some trait, quantitative trait, that's normally distributed amongst members of the population. And so because we're in Portland, I put a bird on it, and we use finches as an example. So say this trait is beak size in finches. All right, so now we're going to assume that this trait is also related to the resources that the organism is feeding on. So with finches, again, as an example, we can assume big beak finches are eating big seeds, small beak finches are eating small seeds, and now we can put predator and prey together, and we see that the most common phenotypes reduce resources the most, and voila, we have disruptive selection. So almost all of these models assume that there is a linear functional response of the consumer. So what is a functional response? Well, the functional response is pretty important for consumer resource interactions because what it allows us to do is translate resource density into the feeding rate of the consumer. So it's pretty central. And one of the important, at least for linear functional responses, one of these important parameters is the attack rate. So that determines the slope of this relationship. So linear functional responses might be good first order approximations for the functional response for things like fishes, birds, sea otters, but I study snails. And so snails definitely do not have a linear functional response. There's a couple of reasons for this. One is that they have a really long handling time. So it can take a snail, especially the species Nucella austrana that I work on, it can take them over a day to eat a single item of their barnacle or mussel prey. And we know that these handling times cause saturation in functional responses. And so this calls into question whether or not this linear functional response assumption works. Also, our lab recently published a paper where we found that there's also predator dependence in functional responses of these snails. So this happens when individuals spend time interacting with one another rather than eating. And this also causes a nonlinearity in the functional response and makes the functional response dependent not only on the density of the prey, but also on the density of the predators. As we also add all of these parameters, they're likely not independent of one another. So we can imagine that, say, an individual's attack rate might be correlated with, say, its handling time. So if you are eating something a lot, you might have a lower handling time on that. And so we also have to think about how these parameters are correlated with one another. So that brings up this question. So how do nonlinear functional responses and correlations amongst the parameters that define those functional responses influence the strength of disruptive selection? And so to get at this question, what I did was build some mathematical models. And so let's build a model. So we're going to begin with the same the same assumption that we had as far as earlier models, and that's that there's some quantitative trait that exists in the population, and it has a normal distribution. Again, we can think of these finches and beak size. So instead of having a continuous a number of prey available, we're going to assume that there's only two kinds of prey, right? So there's, say, large seed, small seed, and the attack rate of the predator we're going to assume is dependent on its trait value. So for example, a bird around here will have a really high attack rate on small seeds, almost no attack rate on, almost no attack rate on small seeds. And so these are the main underlying assumptions about how individuals are interacting with resources. And then we can come up with a population dynamical model. And so this is it. And so we have an equation for the resource and an equation for the consumer. For the resource, we have logistic growth, and then there's a loss rate that is the consumer's effect on the resource. And so this is called a Beddington to Angeles functional response. And so it incorporates handling time here on the two different prey items. And it incorporates interference competition here. And we put these assumptions of the predator trait distribution and its effects on attack rate into these two functions, and then we take the integral over all of that. For the consumer, we have a linear numerical response, and we also have a linear mortality rate. All right, so we have the model for population dynamics. How does this tell us anything about disruptive selection? So it turns out that you can define these models in a way that if the mean trait value for the population is at 0, that's both the ecological and evolutionary equilibrium of the model. It also turns out you can do that in a way in which that evolutionary equilibrium is also a fitness minimum. And that works out nicely because now we can say, all right, everything's at equilibrium. What if we introduce a mutant population that has a shifted mean? Well, it's going to have higher fitness because the original population is at a fitness minimum. And we can ask how much that fitness changes, how greater the fitness is for the mutant. And that is the measure I'm going to use as the strength of disruptive selection. All right, so we've got a model and stuff. Let's get into these nonlinearities. So we'll start with handling time. So as we increase handling time of a population, how does the strength of disruptive selection change? Well, it turns out that longer handling times lead to a decrease in the strength of disruptive selection. So why is this the case? Well, we can look at the feeding rate of predators as a function of what their trait value is. So if we look at individuals with low handling times, we see that their pattern of feeding rate looks like this. Well, as we increase handling time, we see an increase here at that 0 trait value of the where our mean is. And so that change actually leads to lower disruptive selection, right? Lower difference in fitness between a population that has a mean here and one that's shifted over a little bit. So I was talking about correlations between traits. So what happens if handling time is correlated to attack rate? So we can think, I'm going to consider here a negative relationship between attack rates and handling times. And this might be the case, say, if you have individuals that are specialists. Well, it turns out if we include that and consider some maximum handling time and change the slope of this relationship, as we increase that slope, it turns out that disruptive selection gets stronger. So if individuals have lower handling times with higher attack rates, then that effect of decreasing yeah, this effect of decreasing disruptive selection strength with handling time is weaker. All right, so now we can talk about interference. So it turns out that as you change interference, you actually get no change in the strength of disruptive selection. And I thought this was a problem with my code when I first got this result. And it turns out that it wasn't. So why does handling time have an effect, but predator interference doesn't? This was a big question to me. And so what it turns out is it actually has to do with the way this Bennington-D'Angelis functional response works. So the interference rates are here. And they don't interact whatsoever with the actual trait values of individuals. And so handling time, on the other hand, even though it's not dependent, say, on a trait value, still interacts with those trait values because of the way this function is designed. And so that means that there is an interaction there, even though it wouldn't seem to be the case. All right, so we can think again about what if these traits are correlated with one another. And so we can consider interference being, say, negatively correlated with attack rates or positively correlated with attack rates. And if they are negatively correlated with attack rates, we see that if we change the slope of that interaction, that disruptive selection actually becomes stronger. We can consider also if attack rates are positively correlated with interference rates. And there we see that as that relationship becomes stronger, we actually see a decrease in the strength of disruptive selection. So back to these snails, what's all this mean in terms of whether they should exhibit this mechanism of disruptive selection? Well, they have high handling times, and from this model that suggests that this mechanism should be really weak for these snails. Although they might actually be specialists at the individual level, which would suggest that we don't know what's going on. It's, in terms of interference, it's actually pretty weak in these animals, and also we don't know whether it's correlated with their specific attack rates at the individual level, and so again, who knows. What all this does show is that disruptive selection through interspecific competition is most likely in populations where individual specialists have low handling times on their prey and also low interference rates. We don't really have any data on this. If anyone does, that would be awesome. So I only investigated the evolution of this mean of the consumer trait. So in the future, I would like to look at how maybe evolution might occur in other traits. As I said, this interference effect is really dependent on the actual structure of the function that I used. And so modeling that in alternative ways might give different answers. And then, yeah, as I said, we have no idea really about measuring these parameters and their correlations. There's very little data that exists on that. And so hopefully that will be something that will happen in the future. And with that, I'd just like to say thanks to you for being here and listening to me. Thanks to the university for giving me money to come here. And thanks to the National Science Foundation for paying me. All right, thanks.